In game theory, player's strategy is any of the options he or she can choose in a setting where the outcome depends not only on his own actions but on the action of others. A player's strategy will determine the action the player will take at any stage of the game. The strategy concept is sometimes confused with that of a move. A move is an action taken by a player at some point during the play of a game. A strategy, on the other hand, is a complete algorithm for playing the game, telling a player what to do for every possible situation throughout the game. A strategy profile is a set of strategies for all players which fully specifies all actions in a game. A strategy profile must include one and only one strategy for every player. Strategy set. A player's strategy set defines what strategies are available for them to play. A player has a finite strategy set if they have a number of discrete strategies available to them. For instance, in a single game of rock, paper, scissors, each player has the finite strategy set, rock, paper, scissors. A strategy set is infinite otherwise. For instance, an auction with mandated bid increments may have an infinite number of discrete strategies in the strategy set, $10, $20, $30. Alternatively, the cake-cutting game has a bounded continuum of strategies in the strategy set, cut anywhere between 0% and 100% of the cake. In a dynamic game, the strategy set consists of the possible rules a player could give to a robot or agent on how to play the game. For instance, in the ultimatum game, the strategy set for the second player would consist of every possible rule for which offers to accept and which to reject. In a Bayesian game, the strategy set is similar to that in a dynamic game. It consists of rules for what action to take for any possible private information. Choosing a strategy set in applied game theory. The definition of the strategy sets is an important part of the art of making a game simultaneously solvable and meaningful. The game theorist can use knowledge of the overall problem to limit the strategy spaces, and ease the solution. For instance, strictly speaking, in the ultimatum game, a player can have strategies such as reject offers of, accept offers of. Including all such strategies makes for a very large strategy space and a somewhat difficult problem. A game theorist might instead believe they can limit the strategy set to reject any offer X, accept any offer greater than X, for X in pure and mixed strategies. A pure strategy provides a complete definition of how a player will play a game. In particular, it determines the move a player will make for any situation he or she could face. A player's strategy set is the set of pure strategies available to that player. A mixed strategy is an assignment of a probability to each pure strategy. This allows for a player to randomly select a pure strategy. Since probabilities are continuous, there are infinitely many mixed strategies available to a player. Of course, one can regard a pure strategy as a degenerate case of a mixed strategy, in which that particular pure strategy is selected with probability 1 and every other strategy with probability 0. A totally mixed strategy is a mixed strategy in which the player assigns a strictly positive probability to every pure strategy. Mixed strategy. Illustration: consider the payoff matrix pictured to the right. Here one player chooses the row and the other chooses a column. The row player receives the first payoff, the column player the second. If row opts to play A with probability 1, then he is said to be playing a pure strategy. If column opts to flip a coin and play A if the coin lands heads and B if the coin lands tails, then he is said to be playing a mixed strategy, and not a pure strategy. Significance: in his famous paper, John Forbes Nash proved that there is an equilibrium for every finite game. One can divide Nash equilibria into two types: pure strategy Nash equilibria and Nash equilibria where all players are playing pure strategies. Mixed strategy Nash equilibria are equilibria where at least one player is playing a mixed strategy. While Nash proved that every finite game has a Nash equilibrium, not all have pure strategy Nash equilibria. For an example of a game that does not have a Nash equilibrium in pure strategies, see matching pennies. However, many games do have pure strategy Nash equilibria. Further, games can have both pure strategy and mixed strategy equilibria. A disputed meaning during the 1980s, the concept of mixed strategies came under heavy fire for being intuitively problematic. Randomization, central in mixed strategies, lacks behavioral support. Seldom do people make their choices following a lottery. This behavioral problem is compounded by the cognitive difficulty that people are unable to generate random outcomes without the aid of a random or pseudo-random generator. In 1991, game theorist Ariel Rubinstein described alternative ways of understanding the concept. The first, due to Hisani, is called purification, and supposes that the mixed strategies interpretation merely reflects our lack of knowledge of the player's information and decision-making process. Apparently random choices are then seen as consequences of non-specified, payoff irrelevant exogenous factors. However, it is unsatisfying to have results that hang on unspecified factors. A second interpretation imagines the game players standing for a large population of agents. Each of the agents chooses a pure strategy, and the payoff depends on the fraction of agents choosing each strategy. The mixed strategy hence represents the distribution of pure strategies chosen by each population. However, this does not provide any justification for the case when players are individual agents. Later, Aumann and Brandenburger reinterpreted Nash equilibrium as an equilibrium in beliefs, rather than actions. For instance, in rock, paper, scissors, an equilibrium in beliefs would have each player believing the other was equally likely to play each strategy. This interpretation weakens the predictive power of Nash equilibrium. However, since it is possible in such an equilibrium for each player to actually play a pure strategy of rock, ever since, game theorists' attitude towards mixed strategies-based results have been ambivalent. Mixed strategies are still widely used for their capacity to provide Nash equilibria in games where no equilibrium in pure strategies exists. But the model does not specify why and how players randomize their decisions. Behavior strategy. While a mixed strategy assigns a probability distribution over pure strategies, a behavior strategy assigns at each information set a probability distribution over the set of possible actions. While the two concepts are very closely related in the context of normal form games, they have very different implications for extensive form games. Roughly, a mixed strategy randomly chooses a deterministic path through the game tree, while a behavior strategy can be seen as a stochastic path. The relationship between mixed and behavior strategies is the subject of Kuhn's theorem. The result establishes that in any finite extensive form game with perfect recall, for any player and any mixed strategy, there exists a behavior strategy that, against all profiles of strategies, induces the same distribution over terminal nodes as the mixed strategy does. The converse is also true. A famous example of why perfect recall is required for the equivalence is given by Piccione and Rubinstein with their absent-minded driver game.